today's topic of discussion is the oxidation, and you can see from this view graph that there are different types of layers that we use for making a discrete device or an IC. They are say gate oxide, then there can be field oxide, the polysilicon gate or some dielectrics, and finally, the metal layers. And we see that so far as the thermal oxide is concerned, it can be field oxide or the gate oxide, as is evident from this view graph. The main function of the gate oxide is that under which a conducting channel is formed between the source and the drain, and also there is a field oxide which provides isolation among the devices. And also you see that apart from this gate oxide and field oxide, there can be dielectric layer, and this dielectric layer is used for insulation between conducting layers, for diffusion and ion implantation masks, for capping doped films to prevent the loss of dopants, and for passivation to protect devices from impurities, moistures and scratches. Here in this diagram you can see that this is the dielectric layer, silicon nitride is deposited at the top throughout the devices to prevent this kind of scratches or to protect the devices from impurities, moisture, etc. Another important layer you see is the polysilicon layer. This blue region is the polysilicon layer, and this polysilicon layer are nothing but the polycrystalline silicon, which is used as a gate electrode material in MOS devices, a conductive material for multilevel metallization, and a contact material for devices with swallow junctions. And the last one is the metal film, which is used to form low resistance interconnections, ohmic contacts between the metal and semiconductor, and rectifying metal semiconductor barriers. And in this case, in later on we will find that aluminum and silicides are widely used for making the metal films. Now, so far as the oxidation is concerned, high quality native oxide on silicon is used basically in semiconductor technology, and it acts as insulator and as a barrier to diffusion and ion implantation, and in p-n junction it defines the junction area also. Now, the oxidation can be made two types. There can be two type of oxidation. One is the dry oxidation and the second one is the wet oxidation. So, depending on the source of oxygen available in the oxidation process. For dry oxidation, generally oxygen, high purity oxygen gas is used, whereas for wet oxidation high purity water vapor or steam is used. So, depending on the nature of the source that you use for an oxidation process, it can be termed as a dry or wet oxidation. Then you see that there are some important properties of SiO2. It reduces the surface state density of silicon, and you know that if you keep a silicon substrate open in normal laboratory atmosphere, you will find that some dangling bonds are formed on the top taking the aerial oxygen, and it is very prone to oxides. So, a large number of interface traps will be formed in the surface state density will be quite high because of such dangling bonds. So, with the application of SiO2 on silicon, you will find that it can reduce the surface state density, and it can be grown with good control over interface traps and fixed charge to control the leakage current of the junction device and formation of stable gate oxide for field effect devices, below which the conducting channel is formed in a MOS device. So, these are the important properties of SiO2, and you see that so far as the oxidation is concerned, various methods are used for oxidation. One can be thermal oxidation, another can be electrochemical anodization, third one can be plasma reaction, and in your textbooks you will find that a large number of oxidations processes are there using which you can make oxidation. But among these three, thermal oxidation, electrochemical and plasma reaction, we shall find that thermal oxidation is the best one, because this thermal oxidation provides the highest quality oxides with lowest interface trap states. So, in that sense the thermal oxidation is the best one an option that can be available. And this is true for SiO2 system. For silicon, SiO2 is a stable oxide, it makes the interface traps very low and it is very stable. And then what about gallium arsenide? What about gallium arsenide? What happens if gallium arsenide is tried to oxidation? Now, you see that since in the gallium arsenide lattice there are two types of atomic arrangements, one is gallium, another is arsenic. So, because it is a binary semiconductor. So, you will find that always it will lead to non-stoichiometric films. It is non-stoichiometric and you see that Ga2O3 or As2O3, that means the gallium oxide or the arsenic oxides are formed. It gives to very poor electrical insulation and semiconductor surface protection. So, these are not used because though it is the native oxides for gallium arsenide. However, these oxides lead to Fermi level pinning, which is very important in the device application, and because of the Fermi level pinning you will find that a large number of surface states are formed on the gallium arsenide and which prevents processing of the gallium arsenide based MOS devices. So, that is important characteristics and basically this is the negative feature of the gallium arsenide oxidation. So, apart from non-stoichiometric, poor electrical insulation etc., the Fermi level pinning is very important, which gives rise to surface states and which prohibits gallium arsenide based MOS devices application. Now, this is a typical oxidation reactor. You see that in oxidation reactor there are many components available in the oxidation reactor. One is the resistance heater, which is used to heat the substrates. There is a quartz board on which the silicon wafers are placed vertically. You can find that a large number of silicon wafers are kept here in the vertically in a vertical position on the quartz board, and oxygen or H2O is passed through the quartz reactor, and depending on the source you can say that whether it is a dry oxidation or it is wet oxidation, and this oxygen or water vapor is transported to the reactor site by using a carrier gas, which may be nitrogen, which may be argon. It must be a gas having inert quality, and the loading end through which you will load the silicon wafers onto the vertical quartz board inside the reactor. You see that the loading end is fitted in a vertical hood, and the arrow gives the direction of the filtered air which is coming through the above and passing through the lower end. So, making this portion free, relatively free from the dust or the particulate matters. So, that means thereby reducing the contamination of the wafers during the loading or unloading process. So, essentially it is basically a fused quartz tube furnace, and you will find that for diffusion, for oxidation, for doping, this kind of a furnace is widely used, also for the processing of during the rapid thermal annealing, and this quartz tube furnace tube is heated through some resistance heater. Here it is resistance heater is used, or in some cases the induction type or lamp heating furnace one can make. And you see that this reactor for oxidation, if we describe in detail, that apart from a resistance heated furnace, a cylindrical fused quartz tube containing the silicon wafers held vertically in a slotted quartz board, that is shown by these blue vertical lines. These are basically the silicon wafers. It can be 2 inch, 4 inch, 6 inch diameter, and source of dry oxygen or pure water vapor, that is shown on the left side of this diagram. Loading end is housed in a vertical flow hood where a filtered flow of air is maintained. The hood reduces dust and the particulate matters in the air. surrounding the wafers and minimizes contamination during wafer loading that we have discussed earlier. Now, one cannot think of the processing in a normal room, because clean room is essential in making any device processing. All kind of processing is made on a clean room. A clean room is a room, it is free from any dust particle or particulate matters. So, problem with the dust particle which is incorporated into the gate oxide, it can result in enhanced conductivity and cause device failure due to low breakdown voltage, because it acts as an impurity, or it can disrupt single crystal growth of an epitaxial film, causing the formation of dislocation. And this is the presence of this particulate matter or dust is severe for lithographic process, as we shall see later on, that essential clean room is a must in case of a lithographic process. Because you see that if there is a particle or a dust here, so what will happen, that this will constrict the flow of the current, and also here you will see that it will interconnect between this blue region and this blue region, it will act as a conducting, and also it will give rise to some defect. So, you see that depending on the position of the dust particles, since the dimension is very narrow of the less than 1 micron. So, this dust particle can cause havoc during the semiconductor processing. So, you must have a clean room. Now, how to define a clean room? There are two systems using which we can define a clean room. One is the English system, another is the metric system. In English system, this maximum allowable number of particles is 0.5 micron. You see that it is 0.5 micron or above, and per cubic feet. So, if you have a particle above or equals to greater than equals to 0.5 micron per cubic feet, then you can see that that is the maximum allowable limit, and if it is greater than that, then you cannot term that it is a clean room. That means, the size is very important here, 0.5 micron or greater. Now, what is the definition of a class 100 clean room? In a class 100 clean room, you see that the dust count of 100 particles per cubic feet with particles diameter of 0.5 micron and larger. So, you see that if you have a clean room, then you can say that it is a class 100 clean room if the particles, dust particles, or count for the particles is 100 particles per cubic feet. So, in 1 cubic feet of air you can have at the maximum 100 particles. Then what is the dimension of the particles? Dimension of the particles is greater than equals to 0.5 micron or large. That means, either it can be 0.5 micron or larger, and maximum allowable particles are 100 per cubic feet. So, this is known as the class 100 clean room. Or in metric system, you see that it is a logarithm of the maximum allowable number of particles, and the particle size is same in this case also, it is 0.5 micron and larger per cubic meter. So, in metric system it is per cubic meter, and in English system it is per cubic feet. Now, what is the class M 3.5? M stands for metric, 3.5, it means 10 to the power 3.5 or at the most 3500 particles per cubic meter, it is allowed. So, a class 100 clean room is equivalent to class M 3.5 clean room. So, these two clean rooms are essentially equivalent, that means class 100 and class M 3.5. Why? Because the number of particles, 100 particles per cubic feet is equal to 3500 particles per cubic meter, and the dimension of the particle in both the cases are same, it is 0.5 micron or larger, that means in diameter. So, there can be 1000 class, there can be 10,000 class, So, different kind of classes are available to obtain a clean room, and the efficacy of a clean room will be proved during the process of lithography. In this case, you see that the system uses microprocessor to regulate gas flow sequence. So, that means here if you come down to the reactor for the oxidation, this is basically a microprocessor control system, and here you see that to control the automatic insertion and removal of wafers, that means here the automatic insertion and removal of wafers, that is done by the microprocessor control. And to regulate gas flow sequence means this is the gas flow sequence, either it can be oxygen or it can be water vapor, but it must be carried over by the carrier gas, and what is the flow rate of the carrier gas, how long it will flow. So, everything will be settled by the microprocessor control, and in this case you see that apart from this gas flow sequence and automatic insertion and unloading of wafers, temperature you have to increase, because the temperature required in this case is normally 900 to 1200 degree centigrade. This is the temperature required for the oxidation. Now, to ramp the temperature up to highest temperature, to ramp the temperature up to say the oxidation temperature, you have to ramp the temperature. Why? Because otherwise if there is a sudden change of temperature, there will be thermal shock to the wafers and you will not be able to avoid warping of wafers. So, that means there can be some cracks etcetera, hair like cracks also, and that is the warping, and to avoid warping you have to ramp the temperature very slowly. So, from room temperature, say your room temperature is 27 degree centigrade, from 27 degree centigrade to say 1000 degree centigrade, you have to ramp the temperature very slowly. So, that you can have here from 27 to 1000 degree centigrade, you can avoid the warping of the wafers, and to maintain the oxidation temperature within plus minus 1 degree centigrade. So, it is very important, if you need say 979 degrees centigrade or 1100 degree centigrade temperature. So, it must be plus minus 1 degree centigrade, plus minus 1 degree centigrade. So, such kind of precision is required in case of a oxidation system. And again, when the oxidation is completed, then to ramp the temperature down to room temperature from say 1100 degree centigrade or 979 degree centigrade or 1200 degree centigrade, to ramp down the temperature you have to use the microprocessor. So, essentially we find that the oxidation furnace which is used in case of the oxidation process, it must have some computer control or microprocessor control, using which you can load unload the wafers, you can ramp the temperature up to the oxidation temperature which is quite high, to keep the temperature at that point very precisely up to plus minus 1 degree centigrade, then loading unloading of the wafers to control the gas flow, the timing and the flow rate etcetera, all such thing, and when it is over, the oxidation is over, you have to ramp down the temperature from the oxidation temperature down to your room temperature. All such jobs are processed by the microprocessor or in a computer control system. Now, it is very interesting to have the kinetics of growth, because you see that when Si2 is grown on a silicon, silicon is consumed, and we shall see that if you want T thickness of the oxide film, T thickness of SiO2, if you need, so 0.44 T of silicon is consumed. So, that is very important thing, and if we discuss the kinetics of growth of silicon oxide, you will find that this silicon dioxide interface moves into the silicon during oxidation. So, if this is the interface, this is the dotted line is the original silicon surface, this dotted line is the original silicon surface, and this original silicon surface is basically moves downward. So, that means as the SiO2 is grown, this interface comes down slowly. If a silicon dioxide layer you see of thickness x is grown by thermal oxidation, what is the thickness of silicon being consumed? So, that is very interesting thing, and the values are given. The molecular weight of silicon is 28.9 gram per mole and the density of silicon is 2.33 gram per centimeter cube. The corresponding values, that means the molecular weight of silicon dioxide is given as 60.08 gram per mole and 2.21 gram per centimeter cube is the density of SiO2. So, obviously, you see that the density of SiO2 is less than the density of Si. Si density is 2.33 gram per centimeter cube, whereas for SiO2 it is 2.21 gram per centimeter cube. So, obviously, if you compare with the silicon, the porosity is larger in case of SiO2. Now, with this value, let us consider that how this SiO2 layer is grown. In this case, the SiO2 layer is grown. Suppose you have Si, which is nothing but the solid, it reacts with oxygen, which is gas, and SiO2 is formed, which is obviously solid. Or you can have silicon substrate, which is a solid material, and it reacts with it reacts with water vapor, which is basically the gas, that means the steam is used. So, here you see SiO2 solid is formed, and along with this SiO2 there will be hydrogen gas. So, depending on the source, in this case you see that the source is oxygen, no hydrogen is there. In this case the source is the water vapor or the steam, hydrogen gas emits, and obviously, because of the presence of hydrogen gas, you see from this reactor that to vent. Now, vent means this hydrogen must pass out from the quartz tube reactor to the scrubber before sending it to the atmosphere, and in the scrubber there can be some charcoal maintained at a particular temperature, heated charcoal is there, and the hydrogen is passed through that heated charcoal and finally to air. So, not directly it is sent back to the atmosphere. Okay. So, in this case you see that depending on the source of the oxygen, there can be the presence or the emission of hydrogen gas or not. Now, in this case, if we consider this problem that if a silicon dioxide layer of thickness x is grown by thermal oxidation, then what is the thickness of silicon being consumed with this value. So, let us calculate, say the volume of 1 mole of silicon, volume of 1 mole of silicon, if we write, then you have to write that molecular weight of silicon by the density of silicon. Now, what is the molecular weight of silicon? It is given 28.9 gram per mole. You see that it is given here, it is 28.9 gram per mole. And what is the density of silicon? It is also given 2.33 gram per centimeter cube. Now, with this value, if we take the final result, that means 28.9 by 2.33, you will get it is 12.06 centimeter cube by mole. Okay. So, with this thing, with this value we can calculate this volume of 1 mole of silicon. Later we shall see that what is the volume of 1 mole of silicon dioxide. The volume of 1 mole of silicon dioxide, here also we can calculate by the same ratio. You see that here we have taken the molecular weight of silicon to the density of silicon. Here we shall take the molecular weight of SiO2 by the density of SiO2, and in this problem you see that it is given that it is 60.08 gram per mole. So, it is 60.08 gram per mole to the density of SiO2 is 2.21 gram per mole. So, it is 2.21 gram per centimeter cube, and with this value we can calculate the volume of 1 mole of SiO2 as 27.18 centimeter cube by mole. So, what are the values we get? Here we have obtained 12.06, here we obtain 27.18 centimeter cube by mole, that is for SiO2 and this one for silicon. Next is that since 1 mole of silicon is converted to 1 mole of SiO2. So, we can write that the thickness of silicon multiplied by area, because if you multiply thickness with area you will get the volume, by the thickness of SiO2 multiplied by the area. So, you will get volume of 1 mole of silicon to the volume of 1 mole of SiO2. Now, we have already calculated what is the volume of 1 mole of Si or what is the volume of 1 mole of SiO2. So, now you can write from this equation that if you cancels out the area, thickness of silicon, let us denote it by TSI, to the thickness of SiO2, thickness of the silicon dioxide, and that is equals to volume of 1 mole of Si. Volume of 1 mole of Si is 12.06. So, let us write down as 12.06 divided by the volume of 1 mole of SiO2, it is 27.18, this is SiO2. So, it is 27.18, and if you take the final output, it is 0.44. So, we can write that the thickness of silicon will be 0.44 times of SiO2 thickness. So, that we have started earlier that 44% of the silicon is consumed. So, that means the concept is that if you want to grow 100 nanometer of SiO2, how much silicon is consumed? 44 nanometer of silicon is consumed. Okay. So, that is the kinetics of growth for SiO2, and you see that what is the SiO2 structure? SiO2 structure is basically in a SiO2, a silicon atom is surrounded tetrahedrally by 4 oxygen atoms, and you see that a silicon atom is tetrahedrally surrounded by 4 oxygen atoms, and what are the values of those oxygen atoms? One oxygen atom you see that between oxygen atom to atom, the internuclear distance is 2.27 angstrom. The internuclear distance is 2.27 angstrom, while between oxygen and silicon this distance is 1.6 angstrom only. So, now when such kind of arrangements of silicon atoms surrounded tetrahedrally by 4 oxygen atoms, they are joined, these tetrahedra are joined together at their corners by oxygen bridges in a number of ways to form the various phases or structures of silicon dioxide. So, it depends on how they are joined by the oxygen bridges, and we shall see that this is one type of bridge where the oxygen makes the bridges, or here different types of bridges. So, depending on how they are joined, that means the tetrahedra are joined together at their corners by the oxygen bridges, they form different kind of structures. So, different crystalline structures are possible as mentioned earlier. One such structure is known as the quartz, or SiO2 is also called silica. So, silica can be one form of silica can be quartz, which is crystalline in nature. So, different crystalline forms are available in nature, and one amorphous form is also there. And here you see that depending on the oxygen bridges, here two types of bridges we have shown. One is the here the oxygen bridges made up 6 rings with silicon atoms. So, this is silicon atom. So, you see that 1, 2, 3, 4, 5, 6. Here you see 1, 2, 3, 4, 5, 6. So, these 6 silicon atoms, they made up rings, and this is basically a crystalline structure. This is known as the quartz, and here this is the amorphous structure, because there is no periodic structure. Here a periodic structure is formed, here no periodic structure is formed. Here in all the cases it is made up of 6 silicon atoms. Here you see that there is a tendency to form the characteristics ring, but exactly the structure, no periodic structure is formed. Only 43% space is occupied by SiO2 molecules, and the rest of the space is void. Also, if you compare the density, it is 2.21 gram per centimeter cube. Here it is 2.65 gram per centimeter cube is the density of the quartz form, that means the crystalline form. Here it is the amorphous form, and because of this 43% void space, you can see that, and with this void space what happens, that there can be contamination, impurity. So, in SiO2 amorphous form, you see that there is 43% space occupied by SiO2 molecules. So, almost 57% is void, and this 57% void space, this 57% void space has some bad effect in the sense that there can be impurity diffusion. As it is amorphous in nature. So, impurity diffusion will be there, particularly sodium, and because of this impurity diffusion or interdiffusion of some impurities, the stability of the device or the structure will be very small, and so care must be taken to avoid this kind of a structure if we use this SiO2 for some application in the IC technology. Now, if we model the growth, what is the kinetics of thermal oxidation? We see that let us take a semiconductor sample, and the oxidant species can be oxygen or water vapor, but there can be oxide layer. So, if C0 is the surface concentration and of the species, oxidizing species. Oxidizing species are basically the water vapor or the oxygen molecules, these are the oxidizing species. So, they have to diffuse through this oxide layer, and Cs is the surface concentration at the semiconductor, that means at the interface between the oxide and the semiconductor, this Cs is the surface concentration. So, we can calculate the flux F1 and F2, which will give us some insight about the kinetics of thermal oxidation. And as mentioned earlier, that let us consider that d thickness of oxide is formed already, it can be formed by some other process, or already there is a presence of oxide with thickness d. So, we have to consider two surfaces flux between the oxidizing species and oxide, that means at this interface where the oxidizing species enters the system, and between the oxide and the semiconductor F2 flux we have to consider, because that is the surface where Cs concentration of molecules per centimeter cube is available. So, obviously, if you plot with the distance x versus C the concentration is lower in case of the semiconductor surface compared to the oxide surface, where there is the availability of the oxidizing species is very high. Now, with this idea, so let us consider that F1 is the flux, which we can say that it is equals to d and dc by dx, where d is the diffusion constant of the oxidizing species. That means, oxidizing species maybe it can be oxygen molecules or water vapor, that means steam. Now, this is equals to, we can write d C 0 minus C s by x, as you can find that it is C 0 minus C x by x. So, what is x? X is the thickness of oxide layers already present or already formed. It can be formed by some other process as well. Now, this is F1. Now, what about F2? F2 we can write, it is proportional to the surface concentration, and this Cs you see that it is, this is coming through the diffusion through the oxide layer at the surface of the semiconductor. So, this is we can write equals to k some constant into Cs. Now, what is k? K is basically surface reaction rate constant for oxidation. Okay, so we get two types of thing. One is this F1, another is F2, the two fluxes at the two surfaces, one at the oxide surface, another at the semiconductor surface. Now, at steady state what will happen? At steady state these two will be equal. At steady state you see that what happens at steady state? At steady state F1 will be equals to F2, and say that is we can write F1 is basically this thing. So, d C 0 minus C s by x, and that is equals to k C s, and we can write that F equals to, in this case F equals to d C 0 by x plus d by k. As mentioned earlier that d is the diffusion constant or the diffusivity of the oxidizing species in silicon, and x is the thickness of the oxide layer already formed, and C0 is the surface concentration, and k is the surface reaction rate constant for oxidation. Now, what is the growth rate? This is the flux, this is the overall flux at the steady state. Then what is the growth rate? The growth rate is very important, because finally it is the growth rate which will give us the data for any kind of oxidation, and this growth rate you can see that we can write the growth rate can be A by C1. Okay, so, dx dt is the growth rate. Let us consider that dx dt is the growth rate of growth of oxide with time. It is F by C1. Now, what is C1? C1 is the number of molecules of the oxidizing species in a unit volume of the oxide. So, this is the number of molecules of the oxidizing species in a unit volume of the oxide, and if we divide this flux by this number of molecules of the oxidizing species, then we can achieve the growth rate of the oxide layer. Now, if we divide F by C1, so you see that this is the expression for F. So, just divided by C1, so it will be d C0 by C1. So, finally, we can write that the growth rate dx dt is equals to d C0 by C1 by x plus d upon k. You see that the same thing we have written earlier, that divided by C1 in the previous expression. Now, if we rearrange this equation, this will rearrange the equation, then what we will get? We will get x square plus twice d k into x equals to twice d C0 by C1 t plus tau. Why? Because there will be some boundary condition, as we shall discuss here. You see that what is the value of this C0, because we have used C0 here, and what is the value of C0? If we take that the oxidation of growth, the temperature is 1000 degree centigrade and the pressure is 1 atmosphere, then we can say that for dry oxygen the value is 5.2. For dry oxygen it is 5.2 into 10 to the power 16, whereas for wet molecules or wet oxidation it is 3 into 10 to the power 19. So, this is the value, and it is written over here that at 1000 degree centigrade and at a pressure of 1 atmosphere, 5.2 into 10 to the power 16 molecules per centimeter cube is the value of C0 for dry oxygen, and 3 into 10 to the power 19 molecules per centimeter cube for wet oxygen or wet oxidation. Now, what is C0? Here you see C0 is the surface concentration of the oxidizing species. And another thing is that this C1, value of C1 we have taken as discussed earlier, that C1 is the number of molecules of the oxidizing species in a unit volume of the oxide, and what is its value? Now, its value is 2.2 in dry oxygen, 2.2 into 10 to the power 22. So, this value of C1 is C1 is 2.2 into 10 to the power of 22 per centimeter cube in dry, and 4.4 into 10 to the power 22 per centimeter cube in presence of water vapor. Why it is multiplied by 2? Because you see that during oxidation, if you use one oxygen molecule and if you use one water molecule, in water molecule one atom is there. So, if you need 2 molecules, 1 molecule of oxygen, that means you have to use 2 H2O. So, whatever be the value of oxygen, in case of water vapor, it must be multiplied by 2, because in a water molecule only 1 atom of oxygen is there. However, you need 1 molecule of oxygen. Now, this expression, that means dx dt equals to F by C1 and it is equals to d C0 by C1, what we have deduced till now. It has a initial boundary condition that at x equals x0, it is d0, the value of d0, that means it is the initial oxide thickness at t equals to 0. So, that means we are considering that always there is an oxidation layer, oxide layer formed at the surface of the silicon, and so with this boundary condition we can write this expression, that means x square plus 2 d by k into x plus 2 d C0 by C1 into t plus tau. So, this expression we are achieving, and where tau is given by this expression, this represents a time ordinate shift due to initial oxide layer, because here we are getting an initial oxide layer of d0. So, tau is not 0, tau is some finite value having this because of the presence of d0, you see d0 square etc. And so, it is a time shift, it is a time ordinate shift due to initial oxide layer. Now, this can be written as x square plus a x plus b into t plus tau. So, that means a is written this is replaced by a and b replaces this 2 d C0 by C1. So, that means this is replaced by a. So, we can write x square plus a x, that is equals to, it is replaced by b. So, it is b into t plus tau. Okay. So, a and b can have value like this, a equals to twice d by k and b equals to twice d C0 by C1. Then after time t, what should be the oxide thickness? Then you have to take the value of x equals to d by k root over of 1 plus twice C0 k square t plus tau by d C1 minus 1. So, this is the value of the oxide thickness after time t. So, this t, that means how long we are oxidizing the material, in this case the silicon, it depending on how much it is there, we can have t larger or t smaller. So, we shall discuss both the cases when t is large or when t is small. So, what we are doing, first we have taken a semiconductor and we have considered that a d0 oxide layer is there at t equals to 0, some oxide layer is there. Oxidizing species are coming on the surface of the oxide layer having surface concentration C0. These oxidizing species can be water, vapor, steam or oxygen dry. Then it will diffuse through the oxide layer to reach the semiconductor surface with the surface concentration of Cs, and we have calculated two fluxes here, F1 and F2. At steady state this F1 and F2 becomes equal and we have achieved that F equals to this at steady state. And finally, we have solved this equation to obtain the value of x equals to d by k root over of 1 plus 2 C0 k square t plus tau by d C1 minus 1. And now we shall solve for two cases when t can be small, when t can be large. So, that means for small oxidizing time, what happens when t is small and when t is large. Two distinct cases we shall consider with this relation. That means, with this relation when t is small or when t is large. Now, when t is small, what happens? For small t, you can write that for small t, x equals to d by k into 1 plus 2 C 0 k square t plus tau by d C 1 to the power half, because square root is there, minus 1. So, this is equals to d by k 1 plus 2 C 0 k square t plus tau by, here it is half, power is half. So, 2 will be there, multiplied by d C 1 minus 1. So, this will cancel out, this d will go, and we will find that we can write this C 0 k, because this k will cancel out, C 0 k, 1 k will be there, this 2 will also cancel out, by C 1 into t plus tau. Now, what is this C 0 k by C 1? We can write it as b by a into t plus tau. Okay. Why? Because you see that here we have considered what is the value of b and what is the value of a. Here the value of a is twice d by k, the value of a we obtained as twice d by k, and b is twice d C 0 by C 1, twice d C 0 by C 1. So, if you take the ratio of b by a, you will get as twice d C 0 by C 1 multiplied by k by twice d. So, k C 0 by C 1 is obtained, and this is nothing but this, and we can write b by a into t plus tau. So, that is for the small t. Now, for the small t, we see that this is nothing but a rate limiting factor at early stages of the oxide growth. Surface reaction is the rate limiting factor, and the oxide thickness varies linearly with time, because this oxide thickness x proportional to time. It is a constant. This b by a is known as the linear rate constant, because this is a linear process. Here you see that x proportional to time. As the time grows, thickness increases, and so since it is a linear expression, so this b by a can be termed as the linear rate constant. Okay. Next is that what happens when t is large. When t is large, we shall see that when t is large, it is very straightforward. For larger t, we shall get the expression here is, this is the expression that we obtained. This is the expression for x, and when t is large, basically it is the square root of this thing. So, we can write that for large t, we can write x equals to d by k root over of twice C 0 k square into t plus tau by d C 1, and which boils down to 2 C 0 t plus tau, d is here. So, if we put d inside this root, so 1 d will be there, because in the denominator there is 1 d by C 1 is there. So, it will be root over of this. So, the final expression is x is equals to twice d C 0 t plus tau by C 1 root over of, and that is equals to, we can write x square is equals to b t plus tau. You see that here we have used this d twice d C 0 by C 1 as b, because earlier we have used this b as twice d C 0 by C 1. So, this twice d C 0 by C 1 is nothing but b, and so we can write that it is equals to b t plus tau. And we see that this is not a linear equation, it is basically a parabolic equation, and we shall discuss in the next class that what is the implication of this parabolic expression when large T is there, and because this is a parabolic equation, B is known as the parabolic rate constant, B is known as the parabolic rate constant. So, in the next class we shall consider individually what happens if T is large, or what happens when T is small, or what is the bearing of this oxidation on the different crystal plane, what is the effect of dry oxidation, wet oxidation, how they are differ, those things we shall discuss in the next class. Thank you.